Imagine studying really hard for a test, memorizing every single example problem in the textbook. You feel confident, but then the actual test has completely new problems, and you are lost. What happened? You fell into the trap of memorization, not true understanding. This is exactly the problem of overfitting in neural networks. It is when a model learns the training data too well, memorizing specific examples and even noise, instead of grasping the underlying general patterns. As a result, it performs brilliantly on the data it was trained on but struggles significantly with any new, unseen data. Neural networks, especially deep ones, are incredibly powerful and flexible. They have a vast number of parameters, which are like adjustable knobs. When a network has too many of these parameters relative to the amount and quality of the training data, it has the capacity to perfectly fit every single data point, including random fluctuations or errors. Think of it like drawing a very complex curve that passes through every single dot on a graph, even the ones that are outliers. This excessive capacity allows the model to effectively memorize the training set rather than extracting the meaningful relationships. Factors contributing to this include having a model that is simply too complex for the problem at hand, or not having enough diverse training data to begin with. Training for too long also plays a role, as the model continues to adjust its parameters to fit the training data more and more perfectly, losing its ability to generalize. This delicate balance between model complexity and its ability to generalize to new data is often referred to as the bias-variance trade-off. So, what can we do to avoid this? There are several effective strategies. One primary approach is to simply get more diverse and representative training data. Another is to simplify your model architecture, perhaps by reducing the number of layers or neurons. We can also introduce various regularization techniques or implement early stopping during the training process. The true test of a neural network's usefulness is not how well it performs on the data it has already seen, but rather its performance on new unseen data. This is what we call its generalization error. Minimizing this error is paramount. Techniques like dropout, which randomly switches off some neurons during training, or L1 and L2 regularization, which add penalties for large parameter values, actively encourage the network to learn more robust, generalized features. Data augmentation, where you create new training examples by slightly modifying existing ones, is another clever way to implicitly increase your dataset. Ultimately, the problem of overfitting reminds us that more complexity or longer training is not always better. The goal is to build a neural network that understands the fundamental essence of your data, not just its surface details. By proactively addressing overfitting, you ensure your models are not only intelligent but also truly reliable and effective when faced with the unpredictable nature of real-world information.